So I would like to start off talking a bit about the scope of transport and logistics to set the scene there. Then I would like to talk about transport logistics and basically also logistics 4.0. And then venture into transport optimization, which has been sort of like my methodology background throughout these years of research. And then basically give you some more ideas of what could be beyond logistics 4.0 or 4.0. And then end off with a few brief notes on what I believe to be the educational needs in the world of logistics 4.0. And I would like to acknowledge, give some acknowledgements to all of my colleagues, many of them here in the room today, but also to a lot of external partners who have contributed, also some of them here today, over the, well, actually past more than actually 20 years. I cannot really believe that, but it actually is a bit more than 20 years. The scope of transport logistics. So I think that it's safe to say that without efficient transport and logistics systems, we wouldn't really have the society that we have today. You could say that automated mass production systems actually are able to give us a lot of high-end, really high quality products at even a low price because of efficiency in production. Also, globalization has opened up the world to us in many different ways. One of them being international container transport logistics, which enables us to more or less have a lot of different stuff in our local supermarket at unbelievable low prices. The transport cost of moving a small plastic whatever toy from China into someplace in Europe is extremely low. Also, another point of this could be, for instance, the airline business. We see that this very competitive business within the airlines have meant that we can actually fly almost anywhere on this globe at really affordable prices. And of course, all this actually means that we have a transport sector that is in transport and logistics sector that is really big in scope. Some of the numbers to support that comes here. We have a transport sector that directly employs 10 million people across Europe. That's a lot of people. It's more or less almost double the size of Denmark, right? The transport sector accounts, you say, typically approximately for 5% of the gross domestic product, the GDP. So that's transport alone. If we look to some of the downsides of this, congestion costs actually is about estimated to be about 1% of the European GDP. If we take an example in London, which might also be one of the worst places maybe with respect to this, we actually see that commuters spend more than 2 hours per day traveling between home and work. That's more than 1 working day per week. That's a lot of loss of the efficiency, I think. Then turning to the logistics sector, so now we're broadening this out a bit more than transport. You could say that within the EU, we estimate it to actually represent a market volume of nearly 878 billion euro in 4 years' time ago. In Denmark alone, this accounts to almost 15 billion euro, so more than 100 billions, Danish kroner. Then logistics costs usually is said to be about 10 to 15% of the cost of a finished product. Of course, it varies a lot with one product to the next. An iPad, for instance, the transportation cost of an iPad is really low. There might be some other logistics costs there that are actually much higher. So very often you do actually tend to say 10 to 15%. So what are we seeing these years? Well, we are living through what is called, well known now to be the disruption. In some, especially in technology and engineering, we talk about disruption all the time. I've learned that in social sciences, it's usually called transformational change. It sounds maybe also a bit wider somehow. But disruption and transformational change is certainly also taking place within, and maybe even mostly within the transport and logistics sector. And this is, of course, one of the reasons for being so interested in working in this sector and being really enthusiastic about working with this. So one of the parts here is the digitalization, this guy up here. So turning from analog devices into more or less purely digital, a digital world in more or less every parts of the world, in parts of the sector. One of the examples, of course, could be everybody in here, I'm sure, have heard about connected automotive cars. So actually cars being able to communicate somehow and eventually become driverless. I had a big debate with myself. I should put in drones in this presentation. I think I should eventually. So I actually decided to put in a drone. All the drone innovation due to drones and stuff is also really, really relevant in this area. Although I would say, of course, if you look into the market value of the whole transport and logistics sector, this is a niche, but it's an extremely interesting niche to be in. So let's take a look at supply chain management. Really, really simple, one-dimensional supply chain here, going from supplier into retailer. We have material flow going right here, and we have requirements on the information flow going left. So this is simple. In reality, it's not as simple, of course. We have a lot of drivers of which actually means that we have increased complexity rather than this simple picture up here. We have a lot of different product configurations, lead time requirements. We want to have just in time on all our products. We see desires for customization of products. We see the complex networks. I could also have put up like a multi-dimensional real supply chain up there, and that would have been some intertwined arcs going back and forth here. Where we see a lot of actors being involved. We see a lot of actors being involved. This sound guy is really tricky today. 2PLs, 3PLs, 4PLs, even people are now starting to talk about 5PLs. We see a lot of regulations to the sector from the EU, for instance. We have the globalization coming in, et cetera, et cetera. So this, of course, up here is sort of like an illusion of a supply chain, basically. And this is coming more and more complex over the years. So what is trying to actually go into Logistics 4.0? We will start with talking a bit about Industry 4.0. So this is actually where it starts. And, well, basically it started many, many years ago. So talking about the first industrial revolution was when we shifted from being reliant on animals, human effort, and biomass into using fossil fuels and mechanical power. So that was started basically at the end of the 1800s. Then at the end of the 1800s, sorry, and 1700s up there. So at the end of the 1800s, we had the second revolution starting. And that eventually, over the years and the next decades into this last century, so the 20th century, gave us electricity and certainly also mass production, as we saw, for instance, with Ford Motors. The third revolution started in the 50s and brought us electronics, first generations of ICT and automation, basically. So all the stuff that we have us completely surrounded with today more or less started there, and was, of course, very much with all the sort of like the space program of US and Russia. Then, recently, we've seen moving into this, what we could call the fourth revolution, introducing what is called cyber-physical systems. So that will be integrations of computation, networking, and physical resources, and then also again, as we saw just before, digitalization. So this we refer to as the fourth revolution, and that of course buys into the Industry 4.0. One of the very important part of this is the Internet of Things, IoT also called. So in here we talk about network connection of physical objects, so cyber-physical things. And basically, this can actually light up all our, so you can say, dark assets. So assets that haven't been connected before. While preparing for this, people still continue to refer to a shoe. So this one here, why should that be connected to the internet? You might think, well, of course, if you have really high-end shoes and you actually want to give the manufacturer of this shoe some insights into how you wear it and how you tear it. that could actually also be an example of this. So this goes with wireless, but also actually wired devices. There's a picture over there actually saying that it's more or less anything that could be connected here. We have some estimates from Gartner, Cisco, DHL, I think actually also IBM is involved there, saying that today, in 2016, we have 15 billion devices worldwide being part of this IoT. In just 4 years from now, this will grow to 50 billion devices. This is a really big growth in just 4 years. And then they also state that potentially we could have up to 1.5 trillion devices actually take benefit from being connected. So this is actually what could be the benefit of having, for instance, these pair of shoes being connected. Then, obviously, IoT creates a huge amount of data. There's a big debate and a lot of effort going around also at DTU on big data initiatives. Some people, just to mention this in a really, really short way, some people discuss big data being the unstructured data. So actually having huge amounts of data that are unstructured. That is the most challenging, but also maybe the most exciting and thrilling thing to work with. Whereas the big data, the big amounts of data being structured might not be the same kind of thing. And therefore also some people do not really believe that this is actually big data. But still, in here, in this presentation, huge amount of data is a central issue. So Industry 4.0, or Industrie 4.0, I think, in German. Søren? Yeah. Looks like this. So basically, it's based on the idea that we are connecting all relevant, and that's important brackets here, devices, and creating some intelligent networks throughout the whole value chain, you could say. And we still have increasingly automated production in factories. So basically, we go from what could be called like internal intra-facility networks, so the smart factory is also some of these words that we see, and actually into inter-facility networks, so the smart supply chain going across the different facilities that you might have, or even companies within your supply chain. So the result, again, here is that the complexity of the supply chain will continue to grow, maybe even considerably, over the next years. And that, of course, poses some interesting questions for us here at university, in research, in development, and so on. Let's take a look at this picture here. This is the DHL Trend Research. They published this DHL Logistics Trend Radar. Some of you, I am sure, know about this already. Have seen this before. This is the 4th edition, just recent one. On the right-hand side, we have social and business trends. Over at the right, that was the left-hand side, sorry. On the right-hand side, we have the technology trends. And basically, the radar in here looks at all what a DHL Trend Research think could be really relevant areas to look into further over the next years. So starting from here, you could say that actually what was put up here in the corner, that we have a high impact, so potentially can actually be disruptive to the business. So that would be, let me point here, that would be over here, so the high one here, whereas we have the low down here being something which should just be incremental, some improvements in small steps of different technologies. What I'm interested in here is, actually next slide here, so some of these areas here, anticipatory logistics, I'll come back to, on-demand delivery, omni-channel logistics, big data here, cloud logistics, Internet of Things, self-driving vehicles, all this, as you can see here, actually between the technology trends and also is the social business trends. Although actually also here, over here, the share economy logistics, smart energy logistics, de-stressing the supply chain, also to me is extremely interesting subjects and could also entail a lot of heavy technology development. Let's go in more depth with anticipatory logistics, which is the one which is mostly connected to what I've been doing so far and what I also plan on doing for the next years to come. So basically, this deals with algorithms that are capable of predicting behavior of users or systems via the use of big data. So a couple of examples down here, 3 actually. So this could be prediction of new orders or demand. maybe even before these are placed. So you sit with your computer at home, you already have ordered something, and the supply chain already knows that you are probably going to buy this if we put it on sale or if we link it to some other offer that we have. The benefit seen from a supply chain logistics point of view is, of course, that we can decrease the delivery times and have very cost-efficient distribution, and also have the smart sourcing involved. Maintenance is another area. We actually have worked a bit with that already here at DTU in the windmill industry, wind energy industry. So that could be looking into real-time monitoring of assets, so a windmill, for instance, very expensive equipment, trying to minimize the downtime by actually finding out when should this spare part be replaced. So actually a third example here would be supply chain risk management, detecting risk in trade lanes, and also trying to see if we can actually find or avoid having damages to the goods transported by looking into whatever we learn from this. Then challenges to this, of course, is that access to data, even though that we have big data, we have a lot of data available, it might not be opened to everybody. We also live with that actually every day here at DTU when we are working with industry. That what seems to be very easy in the first place might actually be a bit more complex. And also that opens up questions about data security and privacy issues. So how do we go about working with this? Okay, so transport optimization, as I said in the beginning, is sort of like my home ground here and my approach to actually look into some of these problems from Logistics 4.0. How do we see transport optimization? Well, it's basically this smart graphics little thing up here. We have a problem, we have to define the problem, we do a model, it could be a math model, it could be a simulation model. Then we do an implementation, so it could be, again, some kind of an implementation in a simulation language or a mathematical programming language, whatever. And then that will actually enable us to do some scenario analysis, trying to find out whatever can come out of this. With some different inputs, of course. So a simple example of what is transport optimization. This is sort of like the classical thing, which has such a nice, easy way to be explained. So that was why I put it in here. So the classical traveling salesman problem. I know that half of you almost have heard this 1,000 times, but still, it's such a nice little illustration. I found this small case of a traveling salesman problem. So basically you have a salesman that has to visit, in this case, 12 German cities. He wants to find the shortest tour through these cities. So let's just imagine that you can go directly. You don't have to follow the roads here, just for the sake of convenience. And you might ask, so how hard can this be? It's 12 cities, it can really not be that hard. The question is, couldn't you just list all the possible solutions and then pick the shortest one? Well, let's take a look. So let me just try to show how that can be done here. So basically we have this 12 points here. We start up here. It could be Hamburg probably, I think it was. And then we select to go to this one over here, probably Berlin. Then we are in Berlin and we have to take a decision whether or not to go to probably one of these two because that's the shortest one. But basically we could also go to all the remaining ones. So actually, you could start wondering about how many possible combinations can you have for this small problem. Well, it couldn't really be that many. Well, yes, of course, because you have to also look into that. Well, we have n cities, so every time we have to visit a city, we can actually visit a number of combinations. And that actually is really relatively easy to see, that every time you do you have taken a choice, there's one less. And that actually adds up in a very, very easy way of saying that this is equal to n-1 factorial combinations. So how is that? Well, if in the German example here, 12 cities actually gives you 39 million different possibilities. That's pretty rough for such a small case. If you have a 50-city example, we have 10 to the power of 62 combinations, completely out of the scope. And even if you go to 100, having a company that has 100 customers or 50 customers is not unusual, hopefully, still. So these numbers, of course, are very, very, very high. So what are we doing? Well, actually, we cannot just list all combinations and then find the best one. We would never finish due to the combinatorial optimization, or the combinatorial explosion, sorry. So basically what we do is that we look into operations research, closely linked to transport optimization, giving us a wide range of tools to solve this and a lot of other problems, and much, much harder problems actually, efficiently. So primary research field is transport optimization. Well, as I said, takes departure in methodologies originating in operations research. I focus on looking into trying to propose new efficient methods to solve real-time optimization problems within transport logistics. Specific areas of interest, Søren actually mentioned that in the beginning, real-time optimization of transport planning problems, especially within distribution planning. This is what I'm talking about today. Also have a keen interest in optimization of public transport systems. And yes, I know somebody in the audience think, okay, yeah, that also really must be a really important area. Yes, it is. Optimization of scheduling and resources is one of the parts that we are working with there. This is the only thing that I will mention here about that today. So I am concentrating on this one up here. So the solution methodologies could actually go from exact methods and then certainly on to meta heuristics. It could be dedicated heuristics, simulation methods, and so on. So basically, looking into the operations research tools box and finding whatever it suits this problem, and then having to develop that further, because often it does not suit exactly that problem that you want to solve. So I will give you now a couple of examples here. So actually 4 of applications of transport logistics and optimization. And this is actually where I say now we have talked about what is the 4th industrial revolution and industry 4.0. Now industry 4.0, logistics 4.0 also has been mentioned, and now we want to go maybe a bit a step beyond. So how can we actually put in some of the methodology that I've been talking about in the previous slide here into these domains? So let's start off by dynamic vehicle routing. So this was what I did for my PhD many years ago now. Still is a really interesting area to me, as you will see in a few slides' time. So just to give you an idea of what is the problem, well, in here we do not have the traveling salesman problem, but we do have a vehicle routing problem with 5 customers. And they are known at the start of the day, and they demand service from one vehicle operating from a central depot here in the middle. Then we find via a routing algorithm a route servicing all the customers at minimum cost. So that could look like this here. Going here and that word up here. So that would look like how we start the day. Then at time T1, so during the morning hours maybe, we have some people calling in, so some new customers requiring service. We do what was usually done here, make an assertion algorithm and find the best spot to put in this new customers. In this example, of course, it's a very simple and more or less ideal example here. We just put them in and go on. So at the end of the day, we have the 7 customers received service, and then it's really important to state that the algorithms methods that are used here have to be fast. Whereas what we saw before with the traveling salesman problem, having all these different possibilities or combinations, well, it's really interesting, and you could put a lot of effort in trying to solve this mathematically, but in most cases, in reality, we have some kind of dynamism here, so we are able to actually get the solution out while people are waiting for this. So we have to be able to find out whether or not we can serve them while they are on the phone, you could say, or whatever they're doing with their. They would not like to sit and wait for like 1.5 hours to get a really good solution for you as the operator of this. So the methods has to be able to handle dynamism, and both in terms of the order pool and possibly also in the surrounding infrastructure, as I usually refer to. So infrastructure in this case could be roads. So if you have some kind of a roadblock or maybe just decreased travel speed due to rush hour or whatever, that also has to be taken into account. So replanning basically. So basically here I would like to give you sort of like an insight into what have happened within dynamic vehicle routing during the past 3 generations. So the first generation probably started in the 80s, went on through the 90s, and ended around that period in 2000, where more people started looking at that area, basically. In here, we had dynamic information being applied to the classical static vehicle routing problem. And we assumed that we could have knowledge on positioning, vehicle status, and so on. I remember in the days of the PhD to actually struggle about that, because we assumed that we could get it, and we knew that we would be able to get it in a few years. And then years went on, and it took a little bit longer than we thought in the beginning. But still, of course, we were right in assuming that this would come along. I remember a lot of, I'm looking at Jakob, who's in the business, and I remember a lot of people in the trucking industry saying, yes, but our drivers don't want to drive a truck with a GPS because they feel sort of like over monitored or whatever. And of course, that has changed. I mean, this is another situation today. Maybe they don't like it either today if they start thinking about it, but this is just something that you do. So this is this was the case back then. Then, in the second generation, we saw real-time information from a lot of different sources. We saw a priori knowledge about future requests coming into the picture. We started being able to integrate with more advanced maps and ERP systems, and also advanced fleet management systems. So better getting really good data, so updated data. And also that meant that we saw a lot of research looking into stochastic travel times and things like that. We saw a lot of different meteoristics approaches appearing. One of them also very much here at DTU, ALNS, David and Stefan, being the fathers of that one. So large neighborhood searches. Then I think that the third generation, so this is not the 4.0, but more like the third generation of vehicle routing is about to start, has basically already started, although you don't really see that many, or actually, if any, real papers about what I'm hoping to see in the next few years here. So actually looking into what we call predictive analytics. So taking methods from data science, machine learning, and then try to use that for forecasting of coming events, both on this ERP side, but also in the infrastructure side, sorry. And we certainly will see increasingly sophisticated meteoristics and also math heuristics coming along. This also comes from the development of IT equipment, so hardware, that we now have a bundle of different kernels, cores on each motherboard for even like a desktop computer. So of course this will be happening also as a part of this. Then some research questions. So what's the goal of this? Well, this is to propose efficient but also fast methods to be capable of finding feasible and high quality solutions in the dynamic context. Quality could span from elements, or can span elements such as cost, but also robustness is of course really interesting. Fairness, a lot of other things could be taken into consideration here. So we also see these objectives or the goals of doing this becoming more complex, I would say. So the relevance, of course, should be that we now have an increased need for these methods because they have to be able to solve these very big data-based problems. And it is actually a very important part of the world of logistics. So we did some work there quite many years ago, also together with Oli here in the audience, and actually maybe very much on a sad note, Mayo Solomon, who just died a few days ago, was also part of this very much. So in that paper there, or that work there, we actually looked into how can we define dynamism, how can we actually measure this. This is still being referred to relatively much, I think, even though it's an extremely simple concept. Whereas I think actually what would be very interesting to see here is to look more into how can we describe the entropy of a system. So actually going much broader, trying to take in much more concepts than what we did back then. And then, of course, a priori information. We would like to take in the a priori knowledge on future requests and build that into the algorithms. That is still a very much needed thing in anticipatory logistics, you could say. Just a slide here about some early days of dynamic vehicle routing, just to put it in perspective as what I said before with respect to data and the availability of data. I did a case study in the PhD period on long-distance courier mail, and this entailed looking into pickup and delivery of parcels and letters. And also, that would then be divided so that you had some delivery customers, but up here, the pickup customers would be the most interesting ones. They could either be contract customers, so it would be static ones, so we know them in advance, but it could also be on-call customers, so dynamic customers. So what I did was actually I went out to sit with a long-distance courier mail company for 2 weeks and collected a lot of data. And the way that you collected data back then was to actually get your hands onto the data like printouts. So I carried home a lot of printouts, and then when I went back to DTU, I had to sit down, manually type in all the addresses, timestamps, and so on. And why? Yeah, well, it was not possible in any way into a computer because there was a lot of handwriting involved, and some addresses had been recorrected or whatever. So what we did was that we actually had to type them in. I had to type them in, and we then actually were able to automatically map them into a GIS database and get a real distance matrix. That was, wow, pretty advanced back then. Although that when we started doing that, we found out that still having corrected a lot of this, 10 to 15% of all the addresses were invalid. So we had to go all the way back and find out, okay, where could this small vehicle actually have been at that time. So it also took some manual process, but more or less actually it enabled us to do what is set up here. So trying to say, okay, where did we have these dynamic customers appearing? So marking them and somehow bundling them into some squares. And that was basically some of the, I think, still believe that it was some of the very first experiments within a priori information used for dynamic vehicle routing, at least based on real life data. So the thing that we wanted to ask or answer there was, of course, where is the next call going to appear? And in this case, I mean, in here you could see that this was a business region, and trying to actually build that into the algorithms. So fast forward to today, platooning of trucks. We have right now at the department looked at this over the past few months, and this is actually a very good example of where we are today with dynamic vehicle routing. So basically, this deals with the technological development of sensors and communication technologies have enabled trucks to form convoys of vehicles. And hold on tight now, because distances between trucks can actually go down to 4 to 6 meters. I know that some might have seen some pictures of some trucks going past the Great Bell Bridge that were certainly not 4 to 6 meters between them, but much more. That, I think, had to do with some we don't want this to go wrong kind of things. But basically, you can actually go very, very close. And as some of you might have seen up here, this is not a real platoon. So that's certainly more than 4 to 6 meters between these trucks. But this was just an example. I didn't really have a better picture. So basically, you can say that this idea here could be described as trucks accelerating and braking in unison like a procession of circus elephants. I like that quote that I saw the other day from a popular science magazine. So basically, you have to more or less forget for a minute what you learned in what you were taught in driver's ed. So of course, this is really, really contradictory to what you would do if you were riding a manual truck or a manual car. So basically, why are we doing this? Well, if they go so close, we will have a completely different situation, so we can save a lot of fuel. And some estimates might be on the high side, this one, but it says that you could save up to 15%. And this could also actually bring the first steps towards having the driverless truck. So maybe having drivers resting while they are in the platoon, so maybe not being completely off duty, but being semi-off duty, which means that they might have an addendum to the driver rest rules that we are seeing right now. We don't know. At least this is, next slide actually. So this is just to give you an idea of how such a system could look like. So basically we have a number of trucking operators, 1, 2, 3, and upwards there. So different types of companies, and they have a lot of trucks. Basically in this example here, we have trucking operator 2, which has in this case 4. Some of them goes to form a platoon. So within the same company, the same operator, they are forming a platoon. That could be easy, seen from the point of view that they do not have any conflicting interests. Whereas the other concept here, if you think of that some of the trucks here, maybe one here, go from truck operator 2 to form a platoon together with 2 from trucking operator K. And of course that would be entailing what we call between firm platooning, and would be a much more complex concept to work with. So the planning side of this, well, the planning system should be able to automatically answer questions such as how and when is a platoon formed, when is it profitable to form a platoon, so and also how is the gain profit, especially in this case where we have more than one company, one firm being part of this. How do we distribute this in a fair scheme between the different stakeholders there, so the platoon leader and the platoon followers. And well, obviously, timing issues in having trucks meet in order to be synchronized will be challenging in a world with many manual processes. And as I just stated 2 slides ago, the European Commission is really highly interested in this platooning concept, and have reserved just for one project actually 15 to 20 million euro to have a test case on that over the next few years. They've also reserved a corridor in parts of Europe through at least 3 countries, which is equipped for being able to support these tests. So I know that some people think, well, is it coming or is it not coming? Well, we don't know, it's innovation. So we need to try to find out whether or not this can actually work. At least the EU believes that this is worth sponsoring some development money within. Another example, so leaving dynamic vehicle routing and what that entails for a minute, collaborative logistics, so horizontal collaboration. In this case, we have 2 product supply chains. Again, very simple ones, so excuse me for that, but just for the sake of convenience, I've made 2 very simple ones. We know, of course, that vertical collaboration between the different parties of the supply chain is something that we've seen and become gradually better at doing. But also, actually, the horizontal collaboration is actually now starting to appear very much in logistics literature and development. So basically here we try to have maybe even competing. It could be companies that does not have any common interests, but it could actually also be competing companies with competing supply chains that somehow via a setup can actually work together with the other company supply chain, like going horizontally, trying to look at the same level of the supply chain. So in this small case study here, so I've shortened this very much, but this is from a real project that also some of the people here in the audience have been very much involved in, with a Danish company that has a production sites in several places in Europe, and actually also has a lot of customers around Europe. So what we did there, and actually I had some external people help us with, was to map their transport flows, and this is sort of like a skewed or biased, sort of like a filtered version of this picture here, not mentioning any names here, and then actually doing having some software trying to actually compare the flow of this one Danish company with the transport flow of between 150, 200 other companies that had their supply, all their transport flows into the database to find possibilities to collaborate between the different supply chains. So basically, you could imagine a situation where, it's up here. So we have here with the yellow marked transport corridors here or flows here, that between France and Netherlands, this company that we're talking about here would have partial loads a number of times throughout the week or the month. And we actually found out that looking into the flows of these 150, 200 other shippers, or having the algorithm look into it, of course, that there was some residual capacity on the vehicles going the opposite way. So why go with semi-empty trucks rather than actually try to collaborate? So this is an idea called collaboration, horizontal collaboration. In this case here, we identified two potential interesting transport flows. So one from Croatia to Greece, that one up there, and then that one from France to Netherlands. So in order to have this happen, you have to somehow deal with regulations, and therefore having a neutral trustee is a really important part of this, this concept. So between potential collaborating partners. And basically, having software is not solving everything, but you do actually have to look into how can we actually find the right partner for this. And again, as we saw with the platooning effort there, how can you actually split the profit between the different partners involved in this? This is certainly not easy, especially not having it work in practice, we've learned. One last example, city logistics is also something that I'm really interested in. We know that there's a lot of people moving into cities these years. The UN estimates that in 2030, only 14 years from now, 77% of the world population will be estimated to live in cities. And of course, having this would actually increase the problems that we see with the problem of the last mile, as we call it within freight transport logistics. So basically what you can see up there, we have the last mile being a really, really costly part of the supply chain, of the transport chain. And therefore having even more people, and maybe with decreased travel speeds in cities, will even make this worse. The trends that we see within city logistics is also that we would like our goods faster. So that's contra, of course, to the to actually being able to actually do this. But we would like to have our goods faster. So we see a lot of push for having same-day deliveries, or actually even same-hour deliveries. So that might be why the drones are coming into this picture. And of course, the ramifications of what is going on within the e-commerce side, including omnichannel logistics, as we saw with the DHL trend radar. This is also some of the stuff that we are looking at right now. So summing up for that part here, future research directions. Well, I would like to combine methods from data science and the newest meteoristics and math heuristics for that matter, to actually provide the foundation for tools to actually support what we call predictive analytics. And we also should look very much into the methods to support desire for larger integration between companies, internal production logistics and their transport logistics. So there's a big push from the industry. I know that even some of the people here from the industry says that what they're being told by their customers or clients here are that they would like to take a more holistic view into the transport chain. So looking into integration much more. So basically you could say looking into planning and optimization methods for solving challenges arising within the scope of Logistics 4.0. So that will be the beyond part. Then finally, just a few notes on the future needs to engineering education, at least according to me and what we've been seeing so far here at DTU. So the supply chains, as we talked about, are definitely becoming more complex. And the data issue, sort of like the size of companies is also still growing. And that leads me to believe that we will see that the engineer of today and also actually even more of tomorrow has to be able to have, of course, strong analytical skills to work with, for instance, predictive analytics, and the big data, but also actually have to work, the ability to work with complex engineering systems. And at our department here at Management Engineering, of course, we will be playing a leading role in providing research-based teaching with, for instance, the advanced systems design part of this. So this is not solved only by big data, math, analytics, and so on, but actually also a lot of knowledge on advanced systems design. This actually led us to, as also Søren introduced here in the beginning, to propose this bachelor degree program. Oh, what happened there? 2 years ago it started, so we just had our third intake, and you can see here around this young lady some of the most important parts of this. You can see the network part, the global part here. You can see the management, the data, the strategy, the decision, technology, and economics. All of this actually pushing into looking into systems. And this is some of the master programs that this is directed towards. And again, hopefully you can see that engineering management, transport logistics, I've talked about, also the math modeling and computation masters, are very much based on systems, really advanced, complex systems with a lot of data needing these. And that also goes to the sustainable energy, which I do not know so much about. So this is really important for me to stress that whatever we are doing right now, revising our programs and looking into the continuous development of our programs, we have to look very much into the systems perspective. So that leaves me with saying thank you very much for your attention and listening. So questions?